Welcome back, students. In last lecture, we have seen the effect of inductive effect on chemical shift. Today, we'll study resonance effect and its impact on the chemical shift value. Let us consider this example where we are substituting different X groups like hydrogen, methyl group, methoxy, chlorine, carbon-carbon double bond, then this trimethyl group and the carbonyl group. Look at this image where the methoxy group is there. Methoxy group is showing the electron donating resonance effect while the carbonyl group is showing the electron withdrawing group. Now we'll consider X as a hydrogen and that is the reference compound. So olefin, the chemical shift value for proton HA and proton HB, in that case it is 5.28. That is both the protons have same chemical shift value. But if we substitute methyl group in place of hydrogen, the chemical shift values change. The HA proton, that is alpha proton, shows chemical shift value 5.73, while the beta proton shows the 4.88 chemical shift value. This happens because look at this carbon atom to which we are going to add a carbon atom. So substitution of hydrogen by carbon atom increases the chemical shift value of the proton which is directly attached to that carbon atom. But why there is a decrease in the chemical shift value of beta proton? This is because of the hyperconjugative effect of this methyl group. Hyperconjugation of the methyl group will make this beta carbon atom electron rich, and as a result the proton attached to that carbon atom becomes electron rich and shielded. If methyl is replaced by methoxy, now this methoxy group will exert electron donating resonance effect. The oxygen electron pair is delocalized into this system like this, and the beta carbon atom now gets the negative charge, that is beta carbon atom is electron rich. As it is electron rich, the protons attached to this carbon atom, they are shielded proton. So look at the delta value of beta proton when methoxy is the, or B proton when methoxy is the substituent. The value is 3.85. That is the B proton is shielded proton here, and the alpha proton or HA proton, it is deshielded because at the alpha carbon atom oxygen is going to have a electron withdrawing inductive effect. Therefore, HA proton is deshielded. Got this difference? That is, this is having, this carbon atom is having inductive effect and beta carbon atom receives the resonance effect. That's why B proton is shielded while A proton is deshielded. Same effect of chlorine is there. If we substitute chlorine in place of methoxy, then same thing happens. Beta carbon atom becomes electron rich while alpha carbon atom will be deshielded, or it will be electron deficient because of the electron withdrawing inductive effect of the chlorine. Now compare the values of HA proton when the substituent is methoxy and when the substituent is chlorine. When it is methoxy, the HA proton is having 6.38 and with chlorine it is 5.94. That is, if chlorine is the substituent, then the proton is having slightly shielding as compared to methoxy. The reason is that the directly attached atom here is oxygen in case of methoxy and chlorine. The electronegativities of oxygen and chlorine are different. So oxygen is more electronegative. That's why the HA proton is more deshielded when the substituent is methoxy substituent. Now look at the beta carbon atom or beta proton. The delta value for beta proton is 3.85 ppm when methoxy is the substituent, and it is higher value when the substituent is chlorine. Why this happens even though chlorine is less electronegative than oxygen? Now, in this case, the important effect is resonance effect and not the inductive effect. Even though oxygen is more electronegative than chlorine, still its resonance effect is greater. This is because the size of the oxygen is smaller and it is comparable with the carbon atom. So resonance will be effective resonance here. Electron donation will be effective. That's why the beta proton will be electron rich or it is shielded. As chlorine is larger in size, so chlorine and carbon, their size are not comparable. So chlorine electron donating resonance effect will be comparatively less effective and therefore the proton is de-shielded. Now these two also show similar type of the effect. But when we shift towards the carbonyl group, the alpha carbon atom is shielded while the beta carbon atom is de-shielded. Now reason is that on alpha carbon atom it is the inductive effect, but at beta carbon atom it is the resonance effect. Now this acyl group will exert a electron withdrawing resonance effect and therefore the beta carbon atom will be electron deficient. That's why the protons at beta carbon atom, that is Hb proton, is de-shielded and its value is 6.8, 6.40. Look at this structure. When methoxy is having the resonance effect, the beta carbon atom gets negative charge, means it is electron rich. And when the acyl group is there, the beta carbon atom gets the positive charge, that is it is electron deficient. So the protons present here are de-shielded protons. Now look at this example, or now let us consider the inductive and resonance effects in case of aromatic compounds. This is the example where the substituents are methyl groups and these methyl groups show the electron donating inductive effect. Due to this inductive effect, the delta value of this proton, orthoproton, is 7.03. To a small extent, it will show the hyperconjugative effect. Now let us compare this example with these three examples where the substituents are methoxy, hydroxy, and amino group. Methoxy group will have electron withdrawing inductive effect and electron donating resonance effect on the aromatic protons. So now if we compare inductive effect and resonance effect will be stronger in this case. Methoxy oxygen donates the electrons by resonance and the ortho position becomes electron rich. Therefore, the proton present on ortho position is shielded proton. Its delta value is 6.80. Compare with this compound, the proton is having 7.03 where only inductive effect is present or to some extent hyperconjugation is present. While here resonance effect is present, the proton is shielded. Now let us consider this hydroxy substituent. Again here also inductive effect as well as resonance effect is present, but resonance effect is stronger and the proton, orthoproton, is shielded proton. If you look at the delta value of this orthoproton and this, we'll find that the orthoproton, when the substituent is OH, that is in case of phenol, the proton is more shielded proton. This is because the electron donating resonance effect of OH oxygen is more than the methoxy. You can get the small difference, very minute difference between the electronegativities of the hydrogen and the carbon atom. So due to presence of this carbon atom, electron donating ability of this oxygen and electron donating ability of this oxygen, they are different. This is attached to a more electropositive hydrogen, and this is slightly electronegative carbon atom. So even though both are oxygens, hydroxy OH oxygen or hydroxy oxygen will have more tendency to donate the electrons by resonance effect. Now let us consider the next element, which is nitrogen, which is less electronegative than oxygen. So therefore its electron donating effect is more by resonance, and the chemical shift value for this orthoproton is 6.35. This is highly shielded proton. This means that as electronegativity is decreasing, the electron donating resonance ability of that element is increasing, and more shielding effect on orthoprotons is observed. Let us take these examples where the substituents are electron withdrawing substituent. Nitro group, as carboxylic acidic group is there, nitrile is present, aldehyde is present, and trifluoromethyl group is present. Nitro group is having electron withdrawing resonance effect, and at ortho position the electron deficiency is observed, and due to that electron deficiency the proton gets de-shielded. The delta value is 8.48. Now carboxylic acidic group, nitrile group and aldehyde group, all these exert same type of the electron withdrawing resonance effects. Therefore, the orthoprotons are de-shielded. The extent of de-shielding is little bit different for each case, and therefore the slight differences in the delta values are there. This also proves that the nitro group is more electron withdrawing than carboxylic acidic group, nitrile and the aldehyde group. But all the orthoprotons are de-shielded. So we can make a generalization that if electron donating resonance effect is there, orthoprotons are shielded protons, and if electron withdrawing resonance effect is there, orthoprotons are de-shielded protons. Look at this group, trifluoromethyl group is present, which is having an inductive effect. But the inductive effect of this group CF3 and CH3 is different. Orthoproton here is shielded, while orthoproton here is de-shielded. Both the groups are showing the electron withdrawing inductive effect. Still, due to these electron or electronegative fluorine atoms, the electron withdrawing inductive effect of CF3 group is more, and therefore the protons are highly de-shielded protons. This is very interesting example where we are having all haloarenes, that is iodobenzenes, diiodobenzene is there, dibromobenzene is there, this is benzene, para-dichlorobenzene and difluorobenzene. Let us take benzene as a reference compound whose protons show chemical shift value 7.27. And now we have different halogens substituted on the benzene ring. Iodine and bromine, if we consider, they are less electronegative as compared to chlorine and fluorine. So this is least electronegative halogen, while this is most electronegative halogen. What these halogens are going to do with aromatic compounds? Halogens will have electron withdrawing inductive effect. All the halogens will have electron withdrawing inductive effect. At the same time, all of them will show electron donating resonance effect. Now we know that inductive effect depends on the electronegativity. So fluorine, as it is more electronegative, its electron withdrawing inductive effect will be stronger, while iodine, as it is less electronegative, its inductive effect will be weaker. So we think that the electron donating resonance effect should also go in the same direction, but that does not happen. Let us look at the values. When iodine is present, the orthoproton shows a chemical shift value of 7.40 ppm. As soon as we replace it by bromine, the delta value is decreasing, 7.32. If bromine is replaced by chlorine, still there is decrease in the chemical shift value. It becomes 7.24, and when it is fluorine, it becomes 7. So it is very surprising that even though the electronegativities are increasing, the chemical shift value is decreasing, which is unexpected based on the electronegativities. But very important thing is that the resonance effect of all these halogens. All the halogens are exerting resonance effect and they are trying to shield the orthoproton. But now, as the sizes of these halogens are different, iodine is having largest size and chlorine is having smallest size. Size of the iodine and this carbon, they are not comparable. Iodine is very large size, so the resonance effect is not very effective when larger atom is in conjugation with the smaller atom. But fluorine and carbon atom, their sizes are comparable. So that is why even though fluorine is more electronegative, its electron donating resonance effect is very stronger and therefore it shields the orthoproton. Chlorine is slightly larger in size. Its shielding effect is little bit less than the fluorine. Therefore, chlorobenzene orthoprotons are slightly de-shielded than the orthoprotons of fluorobenzene. So as size is increasing, the effect of resonance is decreasing, and that's why here the inductive effect is dominating when the larger size halogen is present, and when smaller size halogen is present, the resonance effect is dominating. Look at these examples. Now here aliphatic system is there, but the substituents are different. Carbon-carbon double bond is having different substituent. Nitro group is there. Nitro group is having electron withdrawing resonance effect. Due to this electron withdrawing resonance effect, this beta carbon atom will get the positive charge, and therefore the proton present on this carbon atom is de-shielded. Its delta value is 7.31. Now when this substituent is present, oxygen is having electron donating resonance effect. So now this proton, beta carbon atom proton, is getting the electron rich surrounding. The beta carbon atom becomes electron rich, and that's why the proton is shielded proton. Compare this electron withdrawing resonance effect and electron donating resonance effect. Same way you are having a dimethyl amino group which is also showing the electron donating resonance effect. It will shield the beta proton. The delta value is 4.42. Again, you can compare both the protons where electron donating resonance effect is there, where the protons are electron rich protons, but still the delta value of this proton is 4.73, and dimethyl amino proton is more electron rich. Its delta value is 4.42. Now again here the electronegativities matter. Oxygen, it is also showing the electron donating resonance. Nitrogen is also showing the electron donating resonance. Still the values are different. This is because the electron donating ability of oxygen and electron donating ability of the nitrogen, they are not same. As oxygen is more electronegative, its electron donating ability will be less, while nitrogen is less electronegative, its electron donating ability will be more. Therefore, The beta proton in this case is shielded, and in this case it's slightly de-shielded. Look at these examples. These are aromatic protons 7.27. If you compare this with olefinic protons are having little bit less delta value, or they are shielded protons as compared to aromatic protons. Look at this example where a carbon-carbon double bond is in conjugation with carbonyl group. Same thing is there. Alpha carbon atom is less de-shielded than the beta carbon atom. This is because beta carbon atom is electron deficient carbon atom. Therefore, the proton present on this carbon atom is de-shielded proton. At the alpha carbon atom, it is the inductive effect. Olefinic proton, whose delta value should be 5.68, but as soon as we place an electron withdrawing group, whose inductive effect will de-shield this alpha carbon atom, the delta value is increasing. Another example where oxygen is showing the electron donating resonance effect, the beta carbon atom is getting the negative charge, therefore the proton is shielded 4.65. And at this alpha carbon atom, delta value is high. This is because the alpha carbon atom is directly attached to an electronegative oxygen. So delta value is 6.35. So this means that the resonance effect is going to either increase or decrease the chemical shift value depending on the nature of the substituent, whether substituent is electron withdrawing or whether it is electron donating. Electron withdrawing substituent will de-shield the protons, and electron donating substituents will shield the protons. Now, next effect which is affecting the chemical shift value is diamagnetic anisotropy.